Hey everyone, welcome back to Calculus 3. This will be lecture 20 of the course. And in this section we're going to, this will be kind of the kickoff section of the final section of Calculus 3, where we will be discussing, we'll kind of shift our emphasis to integration, and we'll be talking about specifically multiple integration. And so, as I said, I think there'll be about 4 or 5 more lectures probably. And in all of those lectures, the focus will be on integration and some of the very, very cool things you can do with integration when you have functions of more than one independent variable. Okay, so let's go ahead and jump into that. And so we'll call this section 4.1, again, the last section of Calc 3, section 4, and it'll be 4.1, iterated integrals and area in the plane. So we're going to first discuss a different way to calculate the area in the plane using multiple integrals. Okay, and so let's just kind of get loosened up, and we'll start with some interesting facts. So just like we saw with partial derivatives, we can meaningfully integrate a function by considering one of the variables, if there are multiple variables, one of them to be constant and just integrating with respect to the other, right? So this is parallel to the idea of a partial derivative. So just like we saw with partial derivatives, we can integrate with respect to one of the variables while holding the other constant. Okay, so what does that look like? Let's see. Right, so if we're given a partial derivative, okay, f with differentiate with respect to x, so f sub x of xy, and just a simple one, 2xy. So this is the partial derivative of some function f with respect to x, differentiated with respect to x. And so what we can say, so if we're given this, then the full function f of xy is going to be equal to the integral of the partial derivative integrated with respect to x, right? And so we can do that really easily here. And so that's going to be equal to the integral of 2xy dx. Now remember, y in this setting is considered to be a constant. And so we can, pull it outside of the integral just to make that plain. Okay, we could also pull the 2 out, but and so this is going to be equal to y times 2x squared over 2, right, plus some constant, right? And so the way that this works, though, here is that the constant itself is not just a constant. The constant is a function of y, right? And so what you end up with here is yx squared plus a constant, which is itself a function of y, right? So that's the kind of tricky part here. That is the tricky part, right? So what does this mean? So the constant of integration, right, which we've denoted as c of y, is a function of y. So what does that mean? Well, in other words, by integrating the partial derivative with respect to x, we're able to recover the original function only partially. We can't get it all, right? So in other words, by integrating f sub x with respect to x, we can recover f only partially. Right, and so hopefully that makes sense, right? Because I mean, if you think about that, if I had some if this was my original f of xy, you know, and maybe it looked like this, right, then f sub x is just going to be 2. Right, now if I integrate this with respect to x, I'm never going to recover this term, am I? That term is lost, right? And so that's what this means, right? So the constant of integration is not, no, it's no longer just a constant. It's some function with respect to y. It's some function of y, right? And so we can't simply integrate the derivative and get back the original function entirely. We can get a portion of it back, knowing that whatever we haven't recovered is some function of the other variable, right? But hopefully it's intuitive that simply integrating is not going to magically make 2y appear, right? So, and the complete recovery of, you know, of f, it is possible to do that in some cases, but that's going to be something they talk about much later, right? In fact, we may not even get into that in Calculus 3 at all, right? What we're going to be, so let me just write that down. So the complete recovery, of f of xy comes later. Okay, it's going to come later in the course. For now, we are interested really only in extending integration to functions of multiple variables. Okay, so that's going to be kind of our focus. We're not necessarily going to be interested in being able to fully recover the original function from a partial derivative or a collection of partial derivatives. Okay, so let's talk through this idea of iterated integration. So by considering y to be a constant, okay, that's our starting point. By considering y to be a constant, we can apply the fundamental theorem of calculus. To get something like this. Okay, so again, this is back to our previous example. If I integrate 1 to 2y of that partial derivative 2xy, okay, then integrating this, we just saw, was produce x squared y plus some constant, but this is a definite integral now, right? So I'm going to integrate. Now I've got these strange bounds, which we'll get to what this is all about in a second. But what we can do here is we can get something that looks like this. Okay, which is equal to 4y cubed minus y. Okay, now notice, right, notice that the result here is a function of y. Very important. Right, so we had this multivariate integrand, which we want to integrate with respect to x. Now what we did in this example is we had, you know, a constant as the lower limit of integration, but we had a function of y as the upper limit. Right, and when we do this, just kind of in the normal way we treat definite integrals, what we see is that the result is a function of y. Right, we could do the same thing by holding x constant and integrating with respect to y instead of with respect to x. Right, so the idea here is with integrated integrals is that we're going to place functions into the limits of the integration of the integral itself. Right, so and you can do it both ways. This is an example of differentiating with respect to x and ending up with a function of y. You could also differentiate with respect to y and end up with a function of x. Right, so here's kind of the summary. So we'll say both directions work, and here is a summary. so both directions work, and here's a summary. So the first thing you might want to do is say I've got some partial with respect to x. Okay, and I want to integrate with respect to x. So what I'm going to use as my bounds are two functions of y. Right, so this is a function of y. It could be a constant, and this is a function of y, which also could be a constant. Okay, and so when I do that, what I get back is this, right? Integrate, where I have to evaluate it, you know, from the bottom to the top here. Okay, and what I end up with is f of, and this would be the top limit, h2 of y, comma y, minus the bottom limit, h1 of y, comma y. Okay, this is what it looks like when we want to integrate with respect to x. Okay. Similarly, if I want to integrate with respect to y, right, I'm going to start with a partial with regard to y, and here I'm going to have two functions of x as my limits. Again, one or both, either or both of these can be could be constants depending on the setting. And so when I differentiate that, I get back f of xy, and I can evaluate that using the limits of the integration. And what gets spit out here is f of x, comma, and it's going to be the upper bound, g2 of x minus f of x, comma, g1 of x. Okay, and again, this is with respect to y. Oops, I'm going to put that in there. There we go. Okay, right, so this is the setup. This is what we're going to explore, like how this application can be applied to finding areas and what it has in common with the way we think of integration already. Okay, and so important to note that the variable of integration, right, namely the dx or the dy, that if you're integrating with respect to x, then that's what we mean by the variable of integration. If you're integrating with respect to y, that's what we mean by the variable of integration. The variable of integration cannot appear in either limit, right? So if you're integrating with respect to x, it doesn't make sense to have a function of x up here or down here. If you're integrating with respect to y, it doesn't make sense to have a function of y as your limits. Okay, so the variable of integration cannot appear in either limit. Okay, right, so it would make no sense, hopefully this is clear, it would make no sense to write the integral from 0 to x of y dx. Okay, so hopefully that's clear. Try that and see if try to calculate this integral, and I think you'll see that this gets a little bizarre fast. Okay, okay. All right, good. Let's do an example here, and we'll get into more and more of these, but let's start with an example. Let's evaluate the integral from 1 up to x of 2x squared y to the negative 2 power plus 2y dy. Okay, obviously, notice that I do have x, I have a function of x in the upper limit here, but that's fine because I'm integrating with respect to y. Okay, so just to make this plain, we're considering x to be constant and integrating with respect to y. Okay, so how does this work? Well, let's write it down here. So this would be 2x squared y to the negative 2 power plus 2y dy. Okay, so you can break this into two integrals. I think that might be advisable just to kind of make it clear what we're doing. And so that would be 2x squared y to the negative 2 dy plus 1 to x of 2y dy. Okay, and then just to make it doubly plain, right, that the x is constant, we can factor it out of the integral, right? Of course, you don't have to do that. I mean, it's not terribly important that you do that, but it's just to make it plain, right? Just because as you're getting used to this integration of multivariate functions, integrands with both variables in there, but you're integrating with respect to only one of them. You have to be very cautious at the onset just to make sure you're getting the setup right here. And then of course this other one is 2 times the integral from 1 to x of y dy. Okay, can we integrate these? Yeah. Okay, so this first one is this is y to the negative 2 power, so this would be 1 over y when we integrate, right? Okay, and then the bounds are 1 up to x. Let's get that up there. And then this other one, second one, would be 2 times, and then when we integrate y with respect to y, you get y squared over 2. And again, 1 up to x. All right, so let's just consolidate that. 2x squared over y plus y squared, and then the bounds are 1 up to x. Okay, now when we are evaluating these definite integrals like this, now remember we're integrating with respect to y, so y is the variable where we're going to do the substitution, and that's essentially how you get rid of all of the y's in the function, and you end up with a function of x in this case, right? So everywhere you have a y, you're going to plug in x's here, so you're going to get 2x squared over x plus x squared, and then minus 2x squared over 1 plus 1 squared. All right, so you're going to get that. And this simplifies down nicely into negative, let's see, 2x plus x squared plus 2x squared minus 1. Okay. And, oh, sorry, I missed a negative here. Yeah, that should be negative there. Actually, this should be negative everywhere. How did I miss that? There we go. Yes. Okay. And so then that simplifies further down into 3x squared minus 2x minus 1. Okay, and so again, note the result is a function of x. Okay, the result is a function of x. Let's try another one. It's going to be kind of based on this one. We'll take this one a little bit further. Okay, let's try. Okay, we're going to evaluate this now. The integral from 1 to 2 of the integral from 1 to x of 2x squared y to the negative 2 power plus 2y dy dx. Okay, so this is a multiple integral, right? This inner piece here is the problem we just did. We just did this one, right? So what have we done is we've added an integral we want to integrate the function that is the result of this inner integral with respect to these real value limits. Okay, and so can we do this? Oh yeah, you betcha, right? Easy peasy. Right? Basically from above, this inner one's already done, right? So just reference the previous example and you'll see that this inner piece, we got 3x squared minus 2x minus 1, right? So this entire piece here is now this. Okay, that's the part that we just did. And we saw how we did that. Right, now we're just taking the additional step of integrating this function with respect to x, integrating it with respect to x, and having these real valued limits of integration. And so this one is, what do we get here? We get 3x cubed over 3 minus 2x squared over 2 minus x, right? And that's going to be from 1 up to 2. And so we can evaluate this. We just get 2 cubed minus 2 squared minus 2. Okay, minus, and then the whole thing is 1 cubed minus 1 squared minus 1. And so what do we get here? We get 8 minus 4 minus 2 minus 1 minus 1 minus 1. And so basically we get 2 minus 1. 2 minus negative 1. Okay. So this is an example of an iterated integral, right? So you start with an integrand that has multiple variables in it, right? You integrate that piece of it with respect to one of the variables, and then you set your limits of your integration as functions, in this case, of x. Right? And when you do that, when you evaluate this definite integral, you get a function of x. And you then integrate that function with respect to x with real valued limits of integration, and you get a real number. Okay, so you get a real number. Okay, and so we usually talk about this in the sense that this is the inside integral, and then this is the outside integral, right? Inside, outside. This should be pretty obvious. They're usually, so these are typically written without brackets, right? I included the brackets here just to make the structure very plain, but normally we don't include the brackets. These are usually written without the brackets. And let me just give some examples here. So usually you would write it like this, from A to B, and then the interior one would be like g1 of x to g2 of x, and then you're going to have some function. And the order here would be you'd first integrate with respect to y, because you can see these are both functions of x, so it'd be dy, and then you'd integrate the resultant function with respect to x. Right, so this is the dy dx version. The same thing could be done this way. You could go c to d on the outside, and then h1 of y, h2 of y, f of xy, dx dy. Right, so you would integrate with respect to x, plug in these limits which are functions of y. You'd get a result of this inside integral would be a function of y, and then you integrate that function of y with respect to y and plug in real valued limits. Okay, so the inside integral, so you can kind of think of this as, this is the inside one, and then the outside one. Right, so inside and outside. So the inside produces basically a standard integral. Okay, and then the outside, what does the outside produce? A real number. So using this process, you can basically start with this kind of convoluted inside-outside integration setup, but what you end up with is a real number in the end, right? So let's consider. So what we've seen so far is just kind of some very vague examples. Let's do something a little more concrete and get a sense for the value that these things can provide, what the use is. All right, so let's consider an example. Okay. So let's say we want to integrate. Let's say we've got this integral. The integral from 1 up to 2 of the integral from 1 up to x of this guy here. Okay, and so let's draw a picture of what this might look like here. Okay, so let's see. Make it nice and large here. Okay, you've got your x-axis, and you'll have, oops, I want to make it a little bigger. 1, 2, okay, and you've got your y-axis. Okay, now let's say we've got a function here, simple 1y equals x. Okay, and the area that we're interested in, I'll shade here. Let's just kind of do the whole thing here. So we can, so there's no question. So we're interested in this area here. Okay. And so the outside limits, namely the 1 and 2, indicate that x lies in the interval between 1 and 2. So the outside limits indicate that x lies in the interval 1 to 2. Okay. The inside limits indicate that y lies in the interval, well, y is between 1 and x, right? 1 is less than or equal to y, which is less than or equal to x. Okay, now can we see that on this chart, right? So y, the variation top to bottom, is going to be between 1 and x, right? This function, right? So you kind of think of the vertical going like that, right? Okay, so it's going to vary across that. X is going to vary from 1 to 2, right? So it's going to kind of go like that. Now, don't worry too much about those rectangles. Those are just me trying to indicate the direction. Okay, but can you see that this would be, this integral here would actually provide you with this area. Okay. So really, this is just a special type of definite integral. It's an integral in which the integrand is also an integral. Okay. This is just a special type of definite integral, one in which the integrand is also an integral. Right, could we integrate this? You bet. We could do this one. Right, so integral from 1 to 2 and from 1 up to x of dy dx. We could integrate that. Right, and what would we get? We would get the integral from 1 to 2, and then this would be y going from 1 up to x dx. And so this would be the integral from 1 to 2, and then x minus 1 dx. Right, and then this would be x squared over 2 minus x from 1 up to 2. Right, and then so what would you get? You'd get 4 over 2 minus 2 minus 1 over 2 minus 1. Okay, and so this would be, so 2 minus 2 minus 1/2 minus 1, right? So you get a 0 here, 0 minus negative 1/2, so 1/2, right? So the answer here would be 1/2. Now, does that make sense? Is the area of this shaded region 1/2? Yeah, of course it is, right? It's a 1 by 1 cube cut in half on the diagonal, so the area there is obviously 1/2. Okay, perfect. So let's do some more examples. Well, before we do an example, let's talk just a little bit more about how this ties in with the definite integrals we've seen previously. Okay, so previously we talked about area of a plane region. Obviously, we discussed a lot of this in Calculus 2, right, using the integral calculus. And so specifically, though, we had this example where, let's say I have two functions, right? I've got a g1 and a g2, right? And maybe I'm interested in the region from a to b between these two functions, right? So I'm interested in this region. Well, we definitely know how to calculate this area using a standard integral, right? What we would do is we'd say we want to integrate from a up to b, and we want to do g2 of x minus g1 of x, and we're going to integrate with respect to x. Okay, and so we know how to do this one. This one is straightforward. Whatever g2 and g1 happen to be, we could plug those into this expression. We could calculate this. Using the fundamental theorem of calculus, however, we can rewrite this piece. We can rewrite this interior piece as a definite integral itself. So using the fundamental theorem of calculus, we can rewrite g2 minus g1, right, this inside part. We can rewrite that specifically as a definite integral. Okay, how does that work? Well, let's let x be fixed. Let x be fixed and consider y as a variable from g1 to g2. Oh, sorry. Let x be fixed and consider y as a variable for g1 and g2. Right, g1 and g2 are functions of y. So here's what we can write. So g1 of x up to g2 of x dy, right? Well, if I integrate this, if I integrate just dy, I get y, and that's going to go from g1 up to g2, and that is obviously going to be equal to g2 of x minus g1 of x, right? Which is the thing we're interested in rewriting. Okay, that's the thing we're interested in rewriting as a definite integral. Okay, and so then what do? Well, it basically follows immediately from this that you could rewrite this expression using an iterated integral rather than using the difference of the two functions, right? So from this, it follows that, well, what we could do is we could say, I've got this integral from a to b, g2 of x minus g1 of x dx. Well, that's just equal to the integral from a to b of y. This is what we just talked about. Okay, and that's just equal to the integral from a to b of the integral from g1 of x up to g2 of x dy dx. Okay, so that's how we can go from the standard sort of definite integral into this iterated integral. Okay, so that's kind of the setup. That's the setup. That's the idea. Okay, There's like some we'll do some examples here in a sec. There's some housekeeping rules that are really kind of a little bit tricky, right? Things that have to be kept in mind as you're working through these, and common mistakes, right? One of the biggest things that people have the difficulty with is knowing whether it's dy dx or dx dy, right? So usually what I try to do is use a representative rectangle in the region. So placing placing a representative rectangle in the region, placing this in the region can give us the order of integration. Right, so what do I mean? Well, like previous example, if I've got two functions like this, and my representative rectangle looks like this, then that means I have to first integrate with respect to y, and then integrate with respect to x, right? Because this is going to go from a to b, right? So this is where we'll want to use dy dx. If conversely, my functions look like this, right, and it was more like a setup like this, then my rectangles would look like this, and I'd have a delta y, and so there I'd want to use dx dy. Okay. Okay, and let's take this idea and make it just a little more formal by kind of defining some of this a little bit tighter. So definition, and this will be, I guess this will be the definition of the area of a region in the plane. Okay, so two scenarios. The first one, if R is defined by A less than or equal to X less than or equal to B, and g1 of x less than or equal to y less than or equal to g2 of x, where now importantly obviously g1 and g2 have to be continuous on this interval. So where g1 and g2 are continuous on the interval a to b, closed interval a to b, then the area of R is, right, and it's just going to be this guy. It's the integral from a up to b of the integral from g1 of x up to g2 of x of times dy dx. Okay, so that's the case where you're using the dy dx to define the area. Now similarly, you can do the same thing, but in reverse. So here R is defined by A less than or equal to Y less than or equal to B, and H1 of Y is less than or equal to X less than or equal to H2 of Y. Right, and again, these have to be continuous on AB, but then the area would just be the reverse and kind of flip some of this. So you go from A up to B, and then from H1 of y to h2 of y dx dy. Okay. Right, so we've already kind of said this, but then just putting a little more rigor behind it. Let's do some examples. Let's do some concrete examples. Okay. So we want to use an iterated integral to represent the area of, and I'm going to draw a picture here. This is going to be a square region, rectangular region, I guess I should say. So we'll have A to B on the x-axis, and this is the y-axis, and on that axis we'll have c up to d. And so what we're interested in is the intersection here of all these lines. So we're interested in this part here. So we want to write this kind of basic integral as an iterated integral. Okay. And so notice, right, that this length is b minus a, isn't it? And this length here is d minus c. So we already kind of know that the area here, I mean, it's a rectangle, right? It's just going to be base times height or length times width. The area is just going to be b minus a times d minus c. All right, so that's what the area is, but how can we represent this as an iterated integral? Well, you can pick whichever way you want to do it. I'm going to set it up this way, where I'm going to have a delta x like that. Okay, so that means I'm going to start with a dy, right? And so the integration with respect to y has to happen along this from between d and c, right? So my inside integral is going to go from c up to d. My outside integral is going to go from a up to b. And because I've oriented it in this way, it's going to be a dy dx. Okay, so I would say that this is the iterated integral that we want to use to represent this area. Does it actually produce the right area, though? Well, let's see. So if we integrate this, this would be the integral from a to b of y from c up to d dx, right? Okay, and so that means this will be the integral from a up to b, and then this, if I evaluate this inside integral, this is just going to be d minus c, right? Like so. And then can I evaluate this? Well, this is just going to be d minus c times x going from a up to b. And we can see that that produces d minus c times b minus a. Okay, and so that's the same as what we have up above. Just looking at the fact that this is a rectangle, base times height, length times width, that's what you get. And the integral works. Okay, so this is a nice sort of, aha, it works. It does it. It does what we want. It does what's expected in the simple cases. Okay, let's take a look at a much more challenging example. Okay, let's take a look at a much more challenging example. And I think I'll switch pages for this one, just so I'm going to draw this picture and I want to be able to reference it. So here's a more challenging version. Let's use an iterated integral to find the area of the region bounded by the graphs of f of x equals sine of x and g of x equals cosine of x, specifically between pi over 4 and 5 pi over 4. Okay, all right. So I'll try to draw this first. And I mean, it's not too bad to draw, but because it's sine and cosine, bear with me. So we'll start with the sine function. We know the sine function starts down at 0, and then it's going to hit a max of 1 and a min of -1. Right? We're just kind of interested in between pi over 4 and 5 pi over 4, so that means we can just kind of move to the right. Okay, and so let's make this is going to be pi over 2. Right? And so sine finds a max at pi over 2, and then it starts to drop, and it cuts through pi here. Okay, and then it's going to reach a minimum at, so this will be pi, and it's going to reach a minimum at 3 pi over 2, which we'll put over here. Okay, so it's going to be down here by the time it gets to there. Okay, and 5 pi over 4 is captured already, so we're good. Okay, and so this is the sine of x. Okay. Now the cosine of x, it's going to start at 1, if you remember from your trigonometry, and it's going to go down and hit a minimum at pi, right? So it's going to be a minimum over here at -1. So it starts up here, and it kind of comes, and I'll do this in dashed lines so you can tell the difference between them. So it comes down like that, and then it heads back up like this. And that's the cosine of x. Okay. Now what we're interested in is the region between these two. Now it just so happens that these two intersect at pi over 4 and over here at 5 pi over 4. So the region of interest is really this region here. So that's what we want to know the area of. Okay, and so we want to represent this using an iterated integral. Okay. Okay, so can we do this? Yes, this is going to be a straightforward application of the derivation we just went through with the two stacked functions, right? Remember when we talked about a g1 and a g2, you know, and the area between them? This is going to be a straightforward plug and chug of that, right? So the area of the region, well, it's going to be equal to, right, and here's how we're going to set it up. I'm going to set it up with my my delta x running like that. So that means this is going to be set up as a dy dx problem. All right, so I'm going to have my double integral dy dx. Okay, and the inner limit is going to go from cosine up to sine. So it'd be cos x and sine x. And then the outer integral is going to go from pi over 4, right, over here, to 5 pi over 4 over here. All right, so pi over 4 to 5 pi over 4. Now, if they didn't, if the sine and cosine didn't necessarily intersect at those points, you know, but like maybe, you know, you were cutting off your limit of integration there, that would be fine. You could just plug it in, whatever those bounds happen to be. Now, if they cross over, though, then you have to do something different. But in this case, it's easy to just plug those straight in, and then we can integrate this. All right, so this is going to be the integral from pi over 4 to 5 pi over 4, and then it's going to be y evaluated from cos x up to sine x dx. Right, and so that means it's pi over 4 up to 5 pi over 4, and it's going to be sine of x minus cos x. Right, now at this point you're basically back to the g2 minus g1 definite integral that we saw back in Calc 2. Okay, and can we integrate that? Yep, the sine x becomes negative cos x. Right, so you're going to get a negative cos x, and then minus, and then the cos x becomes sine x. And that's going from pi over 4 to 5 pi over 4. Okay. And so now we just have to plug everything in. So let me put that on the next line here. So you're going to have negative cos of 5 pi over 4 minus sine of 5 pi over 4. Okay, and then that whole thing minus negative cos of pi over 4 minus sine of pi over 4. Okay, no big deal, just kind of plugging in those endpoints. Now here's where we have to kind of remember our trigonometry, or, you know, maybe pull out a calculator or a unit circle or something and just look for these values. Now this one, each of these, so this guy here is negative square root of 2 over 2. The sine is also negative square root of 2 over 2. Cos pi over 4 is square root of 2 over 2. And sine of pi over 4 is square root of 2 over 2. So rewriting this, you're going to get so this will be a negative square root of 2 over 2. Okay. Minus a negative square root of 2 over 2, right? So you got to keep the negative straight. It's kind of a mess here. And then this is going to be minus a negative square root of 2 over 2 minus square root of 2 over 2. Okay, right. So what do I end up with? I get a square root of 2 over 2 plus square root of 2 over 2 plus square root of 2 over 2 plus square root of 2 over 2. So I get 4 of them. So that's 4 times the square root of 2 over 2. And so that's just 2 square root of 2. Okay, kind of a long mess there, but that's what you end up with. Okay. All right, so that's straightforward application, but this is a nice example because this is the G2, G1 kind of problem, and you can quickly see how the how the iterated integral is going to give you the same answer, right? That inner integral is just going to evaluate down to the definite integral, or to the integrand of the Calc 2 version of the definite integral. Okay, let's do another example. Let's sketch the region, because I think one of the hard parts here is coming up with what these regions all mean. So let's do an example specifically dedicated to that. So sketch the region whose area is represented by this integral from 0 up to 2, and then from y squared up to 4 dx dy. Okay, so first we'll start by sketching that region, and then let's find another iterated integral using the order dy dx instead, right? So this one is dx dy. Let's rewrite it as a dy dx. Okay, and then kind of as part of this, let's show that they're the same. They have the same value. Okay. All right. Okay. So so we're interested in this integral, and we can kind of, just looking at the limits of integration, we can see that we can see from the inner integral, right, in particular, from the inner integral, we can see that y squared is less than or equal to x, which is less than or equal to 4. Okay. So what does that mean? It means whatever the region happens to be, it's bounded on the left by the parabola, by a parabola x equals y squared. So it's bounded on the left by x equals y squared, right? Because this is integrated with respect to x. Okay. And on the right, of course, by the line x equals 4. Okay. And so then the outer region then tells us that y is going to be between 0 and 2. Right? We know that y is going to be between 0 and 2. Okay, which means that y is bounded below by the x-axis. Okay, it's bounded below by the x-axis, and of course it's bounded above by the line y equals 2, x equals 2. Okay. All right, so let's try to draw this thing. What does this got to look like? Well, there are a number of ways to think about it. 2, 3, 4. 1, 2, 3. Okay, so this is your x-axis, and this is your y-axis. And so we know that x is going to be bounded by the parabola x equals y squared and the line x equals 4. So x equals 4 is right here. And x equals y squared would look like, basically like this, right? It would go through 2 squared is equal to 4. So it would kind of go like this, right? X equals y squared means it's, you know, x is a function of y. So the parabola would be kind of turned 90 degrees, right? And so you'd also have this guy here. And so x is between y squared, which is this line, and y equals 4. Or x equals 4, sorry. X equals y squared and x equals 4, right? So your delta y's would run like this, wouldn't they? Okay, and so that is the, because it's written as a dx dy, that means you would have your delta y's like this. Okay. And then does the other piece work, y being between 0 and 2? Well, it does, right? Because you're only interested in the region up to here, and this would top out at 2, right? So this would be the region that you're interested in right here. Okay. So that's how you would sketch it. That's how you'd sketch this one. Okay, now what is the value of this integral? Can we calculate this integral? Yeah, so this is 0 to 2, and then y squared up to 4 dx dy. And so that's going to be the integral from 0 to 2, and then I'm going to kind of jump quickly into this, and it'll be 4 minus y squared dy. And then we have to integrate with respect to y, and you would get 4y minus 1/3 y cubed. And that's going to go from 0 up to 2. And so you would have 4 times 2 minus 1/3 times 2 cubed minus 0 minus 0. Okay, so it'd be 8 minus 8/3. Okay, and so that's going to be 24 minus 8 over 3, so 16 over 3. Okay, so that's the value of the integral. Okay, and so when we sketch this, that's kind of the point here, is to sketch it. Right, so your x values are going to go from y squared to 4, right? So stretching from this line here over to this line here. And your y variables are going to go, or your y values are going to go from 0 up to 2, right? And so that's going to naturally lay out this nice region here. Now, the main task here is to recast this as a dy dx, right? So same picture. Same picture. Okay, and so again, you're going to have this 4,2 point here. Now this time, however, we're going to have a delta x, right? And so what does that mean? Well, let me switch pages here. Switch pages. So what does that mean? Well, what it means is that, you know, by putting this vertical on here, this delta x vertical, we can see that the constant bounds are going to change from 0 to 2 to instead be 0 up to 4. Right, because this delta x has to go from 0 up to 4. Okay, and what about, so that these are going to be the outer limits. Right. What about the inner limits? Well, the inner limits are going to, right now this is, we've been thinking of this as x equals y squared. So when we solve for y, we instead have y equals the square root of x. Okay, so y equals the square root of x is going to be, give us the out the inner bounds, right? So our inner bounds are going to then run from 0. Y is going to be between 0 and this function, which is going to be y equals the square root of x. So the inner bounds is going to look like that. Okay. Right, so the outer limits change from 0 to 2 to 0 to 4, and the inner limits change from y squared to 4 to instead 0 to square root of x. Right, so the new integral is, okay, so you've got double integral, and this is going to go from 0 to 4, and then from 0 up to the square root of x. Okay, and instead of dx dy, it's now going to be dy dx. Okay, let's calculate this one and see what we get. So this would be the integral from 0 up to 4 of, and then inside here you would get the square root of x minus 0 dx. So I'm just going to write that as 0 to 4 square root of x dx. Okay, and so that integral so this is like x to the 1/2 power, and so we integrate that, we get 2/3 x to the 3/2 power. Okay, and that's going to go from 0 up to 4. Okay, and so you can think of this as 2/3 times 4 to the 3/2 minus 2/3 times 0 to the 3/2. Of course, this whole term is now 0. And so this is just 2/3 times 4 to the 3/2 power. And, you know, there's a couple ways to go about this. I mean, I think the best way is to just take the square root first and then cube it, right? So you get 2/3, and then it's the square root of 4 is 2, so this becomes 2 to the 3rd power. And so you have 2 times 2 is 4, times 2 is 8, times 2 is 16 thirds. Okay, and that's, of course, the same answer as we had previously. So both integrals produce 16 thirds. Okay, so the two integrals, let's put them side by side here. So the first one was 0, the one that was given was 0 to 2, and then y squared to 4, and this was a dx dy. And the second one we just calculated was 0 to 4 and 0 to the square root of 2 dy dx. Okay, so these two integrals produce the same area. They refer to the same region in the plane. Okay. All right. So good, fantastic. That is, I think, a good place to end it. Next time, so this is the starting point for multiple integration, this idea of iterated integrals. And really, all we've done here is we've taken a familiar idea from Calculus 2, the idea of finding a region between two curves, and we've extended it and shown that you can do the same thing. You can calculate the same area using multiple integrals, kind of iterating like this. And then talked a little bit about how the regions need to be defined and, you know, kind of what this is all about. Next time, we'll talk about double integrals and volume. And so we've seen volume certainly in the past already, and now we'll get into other ways to represent it. So, all right, that's a good place to end it, and we'll talk to you all. We'll see you all next time. Take care.